Euler's method. Euler's method is a numerical method for solving a differential equation. The best way to really explain Euler's method is to jump into a problem, but before that we need to know what delta x represents. In Euler's method, delta x represents the step or increment that we're using, which is just the distance moved from the initial value. So our problem says to let y equals f of x be a particular solution to the given differential equation with the initial condition f of 0 equals 2. Use Euler's method with a step size of 1 to approximate f of 2 for the equation dy dx equals 2xy over 3. So we know that we have our point 0, 2, our step size 1, and our equation 2xy over 3. And now we can put this all into a table. The table that we have has a column for x values, y values, slope values, tangent values, new x values, and new y values. To get started, we need to plug in our original x that we were given in the problem, 0, and our original y that we were given in the problem, 2. To find the slope, we need to plug these 2 points into our differential equation. When we do this, we get 2 times 0 times 2 over 3, which is 0 over 3, which gives us a slope of 0. To find the tangent line, we need to plug the values that we just found into the point slope formula. When we do that, we get y equals the slope of 0 times x minus our x value 0 plus our y value 2. To find the new x value, we add the original x value to our step size. When we do this, we get 0 plus 1 equals 1. To find the new y value, we plug the new x value into the tangent equation we just found. When we do this, we get y equals 0 times 1 minus 0 plus 2, which gives us 2. So now we take the new x and the new y, and we do a second row of working it out. So we have the x value 1, the y value 2. We plug this into the differential equation again, which gives us 2 times 1 times 2 over 3, which gives us a slope of 4 over 3. We plug this into the point slope form to get our tangent equation. We get y equals 4 over 3 times x minus 1 plus 2. We add our x1 to the step size, so we get 1 plus 1 equals 2. And since our new x equals 2, and we're trying to approximate f of 2, in order to find the answer, all we have to do is find our new y by plugging this new x into our tangent line. When we do that, we get y equals 4 over 3 times 2 minus 1 plus 2, which gives us our answer 10 over 3. So our approximation of f of 2 for the differential equation is 10 over 3. Newton's law of heating and cooling. This law shows the rate at which an object heats up or cools down. We have a formula for it. It's a differential equation. It's dy over dt equals k times y minus b. K represents our constant of proportionality, and b is our fixed constant. When k is less than 0, we know that the temperature falls, and when k is greater than 0, we know that the temperature is going to rise. So we have a big word problem to work out. Your mom agreed to buy you a milkshake, so she went to the ice cream shop to make the purchase. The temperature of the milkshake at the time of purchase was 28 degrees Fahrenheit. Your mom put the milkshake in the cup holder of her car so that she could deliver it to you at home. The temperature in your mom's car is kept at a constant 70 degrees Fahrenheit. Your mom got stuck in traffic and the milkshake began to melt when 10 minutes had passed. After that 10 minutes had passed, the milkshake warmed to 35 degrees Fahrenheit. Write and solve a differential equation modeling the situation and use it to estimate the temperature of the milkshake when your mom arrived home 20 minutes after the milkshake was purchased. So we need to know what this question is asking. So at the very end of the question, it tells us to write and solve a differential equation modeling the situation. And since we're dealing with temperature, we know that the differential equation is going to be a Newton's law of heating and cooling one. It also tells us to estimate the temperature after your mom arrived home 20 minutes after the milkshake was purchased. So that's what the question is asking. It wants us to write and solve a differential equation using Newton's law of heating and cooling, and it wants us to find the temperature of the milkshake 20 minutes after buying. So what do we know? We know that the original temperature at the time of purchase was 28 degrees Fahrenheit. So that means we have, at time 0, a temperature of 28 degrees Fahrenheit. We also know that, at 10 minutes, the temperature of the milkshake warmed to 35 degrees Fahrenheit. So we know that at time 10, we have a temperature 35. We also know that Mom's car is kept at a constant 70 degrees Fahrenheit. So we know that that is our constant. It tells us in the problem. So that's probably going to be our B value in the equation. We also know that we're finding the temperature after 20 minutes. So we have a time t with an unknown temperature. So using our differential equation formula and what we know, we can create a differential equation. So we're going to say big T represents temperature while little t represents time. So we have d big T over d little t equals k times t big T minus 70, because remember 70 is our constant and therefore it is our B value. Second step is to solve this differential equation. So we have our differential equation. We want to get the big T's on one side and the little t's on the other side. So when we do this, we get 1 over t minus 70, big T minus 70 dt equals k dt. In order to really solve this, we need to take the integral or the antiderivative of both sides, which will give us ln the absolute value of t minus 70 equals big T minus 70 equals k little t plus c. We need to exponentiate both sides to get rid of the natural log, and we get the absolute value of big T minus 70 equals e to the k times little t power times e to the c power. Because we know that when two numbers are multiplied, their exponents add together. We can get rid of this absolute value sign and this e to the c power by replacing that with a constant a. When we do this, we get big T minus 70 equals a times e to the k times little t power. When we add 70 to both sides, we get our equation t equals big A times e to the k times little t power plus 70. And now we have to solve for our k value and our a value. Let me fix that. Ignore that t. We need to find a. So when we do this, we need to have our points. So remember, we had at time 0, we have a temperature of 28. At time 10, we have a temperature of 35. And at time 20, we don't know our temperature. So we can use this first ordered pair right here, 0, 28, and plug it into our formula, or to our equation, to solve for A. So we get 28 equals A times e to the k times 0 power plus 70. And we know that when e is raised to when e is raised to 0, it equals 1. So we get 28 equals a times 1 plus 70. And when we subtract 70 from both sides, we get our a value, negative 42. And now we need to plug this back into our equation to get big T equals negative 42e to the k times little t power plus 70. And now that we've done that, we have enough information to solve for our k value. So we already used the 0, 28 coordinate pair, ordered pair. And so now we need to use our time 10, temperature 35 pair. So we have our equation again, big T equals negative 42e to the k times little t power plus 70. And when we plug in our values, we get 35 equals negative 42e to the k times 10 power plus 70. We subtract 70 from both sides to give us negative 35 equals negative 42e to the k times 10 power. And we divide both sides by negative 42. And that gives us 35 over 42, positive 35 over 42, equals e to the k times 10 power. In order to get rid of this e, we need to use the natural log on both sides. So we get ln times 35 over 42 equals k times 10. We divide both sides by 10 to give us our k value, which is 1/10 ln 35 over 42. And now we plug this back into our original equation, and we get big T equals negative 42e to the 1/10 ln 35 over 42 times t power plus 70. And we can use this equation to find the temperature after 20 minutes had passed. So in order to solve for time 20, we just plug in 20 for our little t, which is right here. And so when we do that, we get big T equals negative 42e to 1/10 times ln 35 over 42 times 20 plus 70 gives us our answer, 40.833 degrees Fahrenheit.